Alright, so let's take a look at statistical hypotheses. Now, these allow us to determine whether there's a statistically significant difference between two groups. Now, the null hypothesis is the hypothesis that there's no difference or relationship between a disease and a risk factor. Example of this might be looking at lung cancer and smoking, and a null hypothesis would state that there is no association between lung cancer and smoking. Now, what do we know about lung cancer and smoking? Great, that there is an association. So, what would that mean? There you go, that we would be rejecting the null hypothesis here. Now, the alternative hypothesis states that there is in fact a difference or relationship between the risk factor and the disease. So, for our lung cancer example, the alternative hypothesis would state that there is an association between lung cancer and smoking. And since we know this to be true, we would be accepting our alternative hypothesis. Now, these hypotheses will show up on various statistical tests, and we'll discuss this more when we discuss outcomes of statistical hypothesis testing. All right, so now let's talk about types of errors when evaluating a statistical hypothesis. When looking at outcomes, you can end up with essentially two results. Either you're correct or you're incorrect. And if we look further at correct results, these mostly occur in two ways. The first way, you state there's an effect, a relationship between a risk factor and a disease, and you're right. The second way is you say there's no relationship, and again, you're right. Simple, right? But let's explore that more deeply using null and alternative hypotheses. So what does the null hypothesis say again? There you go. That there's no association between the disease and the risk factor. Now the alternative hypothesis that says yes, there is an association, opposite view. Let's say you review patient data and conclude, yep, lung cancer and smoking are linked, and you're right. Would you accept the null? Nope. You'd reject it and accept the alternative. Now, just like results can be correct, they can also be wrong, and that's where errors come in. We have type 1 error or alpha and type 2 error or beta. Let's break that down. A type 1 error is when you say there's an effect, but there actually isn't. That's a false positive. You rejected the null and accepted the alternative, but you were wrong. In hypothesis terms, you rejected something true. Type 1 error is marked by alpha. If you check your 2x2 table, alpha is where you find the false positives. Now here's a key stat link. The p-value of your study equals the probability of making a type 1 error. And that p-value, it's often measured against 0.05, the classic significance level. If your p-value is less than 0.05, that means there's less than a 5% chance your finding is random. That's why a lower p-value, a more confidence that your result is real. Now let's flip to the other side, type 2 error. This is when you say there's no effect, but there actually is one. You missed something real. In hypothesis terms, you fail to reject the null, even though it's false. That means you don't accept the alternative, even though it's true. Type 2 error is the false negative marked by beta in your 2x2 table. Beta is where your false negatives hide. Now beta has a counterpart, power, which is 1 minus beta. So anything that reduces beta increases power. Here's a question for you. How do we reduce type 2 error? Exactly, increase sample size. More people, more accurate reflection of the population. That reduces your chance of missing a true effect and boosts your study's power. Now, what exactly is power? It's the probability of detecting a true effect or rejecting the null when it's false. In simple terms, power tells you how good your study is. A high power study means a high chance you'll catch what's real. Mathematically, power we are 1 by data, and that corresponds to true positives in your results. Let's try a fun analogy. You're flipping a coin, null hypothesis, it's fair. Alternative, it favors heads. We flip it 10 times, 6 heads, 4 tails. Is that enough to reject the null? Not really. Power's too low. Now, flip it 1,000 times, 600 heads, 400 tails. Now you've got power, enough to reject the null and say, yep, this coin favors heads. So how do you increase power? Let's count. Increase sample size, reduce data spread, aka variability. Increase precision, increase alpha, increase effect size. Quick tip, reducing spread increases precision, and precision makes it easier to find differences, thus increasing power. Also, yes, If you're willing to increase alpha, you reduce beta. Less beta, more power. Alright, did you catch all that? Let's do a practice question. Researchers are designing a study to test if a new beta blocker reduces side effects and improves survival in MI patients compared to standard care. They want to avoid saying there's a difference when there really isn't one. Which parameter do they want to maximize? A. Alpha, B. Beta, C. 1 minus alpha, D. Power. Answer C. 1 minus alpha. They want to minimize alpha, the probability of a type 1 error, or false positive. So if you minimize alpha, you maximize 1 minus alpha. Now, beta refers to type 2 error, missing a real difference. That's not what they're worried about here. They want to avoid falsely claiming a difference. So they're focused on alpha, not beta. Maximizing power is great, but that's about catching real differences. This question, it's about avoiding false ones. So the correct answer is again C, 1 minus alpha. C. The confidence interval is defined as the range of values in which a specified proportion of repeated sample means would be expected to fall. It is calculated as the mean plus or minus the z-score times the standard error of the mean. And now a z-score describes the distance that a particular data point is away from the population mean in terms of standard deviations. So something that has, let's say, a z-score of 2 is 2 standard deviations away from the mean. There are only a few important things you really need to know about the confidence interval and z-score as they relate to your test. The 95% confidence interval, which is the most commonly used, corresponds to a p-value of 0.05. The z-score for the 95% confidence interval is 1.96, so it's almost 2 standard deviations away. Now, the z-score for the 99% confidence interval is 2.58, or roughly 2.5 standard deviations away. More importantly, here are the practical applications of the confidence interval you should remember. If the 95% confidence interval for the mean difference between two variables includes 0, then there is no significant difference, and the null hypothesis should not be rejected. If the 95% confidence interval for the odds ratio or the relative risk includes 1, then again the null hypothesis is not rejected. Finally, if the confidence intervals between two groups overlap, then these groups are not significantly different. So a meta-analysis is a method of data analysis that looks at pooled data. These studies are great at summarizing the results of multiple different studies, particularly studies that individually would have been underpowered and difficult to draw general conclusions from. When you see a meta-analysis, it usually looks something like this. Here you can see several different studies and their results. This line here is the relative risk line. What does relative risk look at again? Great. It's the association between an exposure and a result. Here we can see if in each study the patients benefited from treatment or not. So in a meta-analysis, you would search for all the studies that pertain to whatever outcome you're hoping to measure. And then you'd combine all the results. This increases the power of your study and makes the evidence more generalizable. There are pretty systematic ways you would go about including or excluding studies for your meta-analysis. But that's a bit beyond what the USMLE will ask you. Just know that oftentimes meta-analyses are combined with systematic reviews. The big limiting factor here is the strength of each individual study, so you'll need to be fairly rigorous in your overall study design. As I'm sure you all know, the old adage, garbage in equals garbage out. If the studies themselves are bad, then they will taint the info the meta-analysis provides. But if the studies are good, then the info will be good. It is fairly high yield for the boards and useful for interpreting clinical studies to understand the differences between these 4 statistical tests. The boards will likely ask about this information by presenting you with a study and asking, what is the most appropriate test to assess this data? The t-test compares the means of two groups. For example, if you're comparing two cohorts based on systolic blood pressure, you would look at their means and use a t-test to determine whether there is a statistically significant difference. The ANOVA compares the means of 3 or more groups. So if you're comparing 5 different cohorts based on their systolic blood pressure means, you would use an ANOVA to test for statistical significance. Basically, ANOVA does the same thing as a t-test but for a larger number of groups. Finally, the chi-square test compares 2 or more percentages or proportions of categorical outcomes. You would use this test when dealing with categorical data that is represented as fractions, proportions, or percentages. For example, the chi-square test would be useful for comparing the proportion of smokers with lung cancer versus the proportion of non-smokers with lung cancer. Now, if your patient outcomes can be codified as ones or zeros, as in this person has the disease or doesn't, so sort of binary coding, then you should think of using a chi-square test. Let's also add a fourth important one, Fisher's exact test. This test checks differences between two percentages or proportions of categorical nominal outcomes. You use it instead of the chi-square test when working with small sample sizes. For example, comparing the percentage of 20 men and 20 women with hypertension. Okay, let's do a question. A study is performed to determine the association between statin therapy and rhabdomyolysis. The findings for 1,000 patients are summarized in the table below. What is the best statistical method for assessing the results of this study? Notice the patients are divided into two groups and the outcome of interest is a categorical variable. Hence, a chi-square test would be the most suitable for determining whether there is a statistically significant association between statin therapy and rhabdomyolysis. Don't be fooled into choosing a two-sample t-test just because there are two groups of patients being compared here. The correlation coefficient R by definition is always between -1 and +1. The closer the absolute value of R is to 1, the stronger the correlation between two variables, either in a positive or negative direction. Can you think of examples of both positive and negative correlations? Well, let's say if the correlation between stroke volume and cardiac output is 0.99, then there is a very strong positive correlation between them. As stroke volume increases, cardiac output also increases. Now, if the correlation between vascular resistance and blood flow is negative 0.99, then there's a strong negative correlation between them. As resistance increases, blood flow decreases. Data with an R closer to 0 looks like this. It's important to notice that R describes the fit of the data about the line, but not the slope of the line itself. The coefficient of determination is simply the square of the correlation coefficient. When used in the context of a statistical model like linear regression, it represents the proportion of variability in a dataset that is accounted for by the model. Values can range from 0 to 1, and as values get closer to 1, the better the model will fit the data. And so let's look at this question. Which of these two graphs would have an R value closer to 1? Well, you should be able to see that in A, the value of the data points are all more closely clustered around the line describing them. C would be an R value closer to -1. Now, statistics is a very important part of decision making. As a physician and as a scientist, it's important to understand these questions not only for the boards but for clinical practice and for interpreting medical and basic science experiments.